Loading the images into the canvas. This document, I'm approaching a couple things a little bit differently. Instead of having a canvas element in the markup ahead of time, I thought this would be a nice opportunity to demonstrate using the create element method of adding the canvas to our markup. So we create our variable of canvas, then document create element canvas. Our name of canvas here is not, we could name that whatever we want, where the element we're creating, we do need to reference it as actually canvas, because that is, we're creating a markup element of canvas as if we had just typed it directly into the markup ourselves. Then we have our context where we take the canvas, get its context, and then we're setting the width and height of the canvas to the entire window. So we're setting it equal to the width of the browser window and the height of the browser window. So we're grabbing those two values as well. To add the canvas finally to our document, we use document.body.appendChild and then specify this canvas element that we have now created. So all of that code simply creates a canvas element, makes it the height and width of the browser window, and then adds it to the markup. That's what that does. And once you have it, if you have future projects, copy paste it from project to project. You don't have to retype it. There's nothing magical or special about it. It's just very straightforward. Create the element, get the context, set the width and height, and if you don't want it to be the full size of the browser, you could certainly use different numbers. And then we use document.body.appendChild. So we have to specify the path of how we are appending it to our document. If we were appending it to a div in the document, so say our markup actually had a div, but we wanted to construct the canvas element through JavaScript, then we would have to use the document.getElement by ID or by tag name and access the div that way and then append it to that element. But that's the basic run through for creating and adding our canvas element to our document. So even if we don't load an image into it, we can pull up the markup afterward and look at it in the browser view source, and we'll see that our markup, which here, body, close body, there is no canvas element, but JavaScript is now creating it and adding it to the body. Loading the image requires us to do a couple more things here, and it looks like I lost a little bit of code. Lost one word during some cleaning or deleting. So I'm not seeing that referenced anywhere else as a variable.
Why is it still working?
So after much deliberation and discussion and research through almighty Google, we've determined that the word var should be used to maintain proper scope of your variables. Otherwise, it just adds the variable as a property to the global document space, which could be problematic. So use the word var even if the starting file today did not have it. So we create a little spot of memory, set it aside, and say it's populated by a new image. Notice that new image uses the capital I in image because we're referring to the built-in image object that is part of the Canvas API. So you need to use the capital I when you say new image. Then we specify the source for that image and reference the current path name in relation to our document. And then to get the image to show up on screen, this does a few extra niceties in that it does not try to draw the image until the image has loaded. But in a slightly simpler slightly simpler version, we could just simply call context and not have any of this stuff. So it's tell the context to draw image. The draw image command is what issues the command to the browser to fill the pixels of the canvas with this image at this X and Y location.
Will that define what?
So one of the key things that I thought, working locally, we could just simply tell the context to draw the image. That is the command to issue draw image. But it's providing a little bit of challenge because locally you can get away with that. But if you are working on a actual live web server where you have to worry about download speeds, you would never want to create your variable, say the path name for that, and then tell it to immediately draw, because across a network it's almost assumed that it will not have been able to load the contents that it needs before you're already telling it to draw. So you would run into failure. So issuing a command to draw image immediately after you've defined the image variable and the source for it is going to cause it to fail because the item will not have been able to be loaded into the browser's memory yet. So then there's nothing for it to draw. So the solution to that is wrapping things up into an onload. So I tell my image.onload, so I'm not even tying it to the whole document or window or any of that. I just say image. So when this image has loaded, then it calls the draw function. The draw function then, and we could just skip having the draw function and just call this line directly after it's loaded. But having the draw function gives you the option of, if you wanted to do more than just draw that image, it separates out the logic into a little cleaner flow. So I would recommend it from that context. So when the image is loaded, it activates draw function. The draw function then tells the context to draw the image, and it draws our image variable object with this source at this X and Y location. This is the minimum parameters for draw image, is image source, X, and Y. You can also put in a width and height if you're so motivated and you want to extend it out. So you don't have to, but you can as part of it. So JSON is JavaScript object notation. That's the JSON. So that it's a different way of encoding data from XML. XML was thought to be the savior of the universe in all things internet related in the mid 2000s. Everyone thought that was going to revolutionize this with XHTML and all these other X branded things that do great and amazing stuff. But JavaScript then developed the JSON format, JavaScript object notation, where instead of using XML, you write things as a JavaScript object. So we can look at this in the same way we looked at the objects that we discussed before spring break, where we have property value associated with an object, and we can have it nested. So we have our main property, and then its value is this array of elements. Then we have element 1, colon, and then that element has a series of properties contained within it. We have property, and then this is a bunch of values. Sometimes it's property in a single item or value, rotated, trimmed, false. But using Flash to generate the sprite sheets is a nice feature that Adobe included with CS6. They licensed an open source software tool from Grant Skinner that he created at his company for their developers to create sprite sheets from their Flash animations, because Grant Skinner is both a person and a company. The company then produced, they made their kind of fame and fortune doing Flash interactive development and content. And they branched into doing HTML and JavaScript as they looked at where industry was heading. And one of the tools they developed was a Spreadsheet Generator that worked from Flash, because all of their animators and artists were used to working in Flash for creating their content. So they used their in-house tool to create their assets. They got contacted by Microsoft to build a HTML5 game, so Microsoft and Internet Explorer could say, see, look how awesome a non-Flash world is, because we don't need Flash, we can do all these cool things. So they developed a number of proprietary tools, which they've now open sourced as the Create.js tool suite. And one of those is the Spreadsheet Generator, which then Adobe licensed and bundled directly into Flash. So you can build your animation in Flash. You can then go to your library, right-click on a movie clip, and choose Create Spreadsheet. It writes a JSON file like we see here, and it then also produces the visual that we can see, where it takes each frame of your animation and then it stacks it together and puts it into one single graphic file. In this case, a PNG. PNG then has a transparent background, so I can load this on top of other artwork and other cool, awesome things like that.
Can you only do it in?
So in the JSON that is constructed by Flash, and other tools will produce similar JSON. This JSON is extremely similar to the JSON that is produced by Texture Packer as a tool. So there's a lot of similarity. I think if we tweak the settings in Zoe, it will also give us a similar kind of JSON file. But what we can do here is go and access a couple numbers that we're going to need. We'll need to know a width and a height. Now we could write JavaScript to access the JSON to extract the width and height from the JSON. So all we have to do is say, here's the image, here's the JSON associated with that image, and now I want you to get the information about that. And we will probably look at some strategies for doing that, but not today. First, we want to just get our images up and running. So if you pay attention to your image as you construct it in your animation tool of choice, whether it's Photoshop, Flash, or Animate Pro, or whatever tool makes you happy, GIF Builder, Movie Maker, I don't know, whatever you use. If you know your dimensions, write it down. If you use a tool that writes out the JSON, use the dimensions it provides to you. Then, what we get to do is we get to use our similar kind of approach here. So I've created the canvas, added the canvas, have my image, and then I'm going to, under set interval, I'm going to call loop, so that I will create a perpetual running loop at what is approximately 30 frames per second. So 1,000 divided by 30, my desired targeted frame rate gives me 30 frames per second. So milliseconds divided by frame rate does equate to getting you the correct result. Now, I'm running into a little problem on fitting one line of code all the way on screen because it's too long. So we're going to take a look at that and study it in a little bit more detail. So we have a whole bunch of variables that are in use that we will need access to. To explain those, we have sx, sy, dx, dy. Number of frames is that was old. We are not using that anymore, so we can probably delete that. I believe I removed all references to number of frames. So we'll don't need that. But we have total number of sprites. Now, total number of sprites does correspond to... So within the image, we'll see that the elf that we're going to be animating, it is a sprite sheet that is 3 rows, 4 columns. So we have column 1, column 2, column 3, column 4, row 1, row 2, row 3. So that gives me a total of 12 sprites that are part of my animation. We know the height and width from the JSON. We know how many sprites. So total sprites 12. frame width, frame height, the size of each frame of my animation. That's the numbers. Those came from the JSON. This comes from studying the graphic and counting it. Number of columns we'll see is 4. 1, 2, 3, 4 columns. So those are the particulars we get from both the JSON and by studying the output sprite sheet that our tool of choice has produced for us.
Where are you calling the road?
So we only need to know how big our graphic is. We need to know how many columns it is. And then we're able to generate our animation from, and how many sprites or how many frames it has. So we know how many frames or sprites. It's the width and height of each individual frame and how many. Now we start out, our current sprite will start out at 0, and then we're going to be working up from that. SX, SY, DX, DY. Those refer to our source X and Y and our destination X and Y. Destination X and Y are where in the canvas we want to draw. So where are we putting this? Source X and Y are where in our image file are we getting our pixel information from. So source position versus drawing position or destination position. Those are the two distinctions that we need. So when we look at the sprite sheet, our source position, where in the sprite sheet are we grabbing pixel information from? That's SX and SY. DX and DY will be where on the canvas are we going to then draw that information. So source information, destination information. Now, when our loop runs, we tell it to draw our image, and then we specify what image, source X and Y, and then the width and height of the area that we are trying to copy. And then we specify where we want to draw it on the canvas, dx, dy, and how big an area, x and y, we want to write into. So these are the full parameters of draw image. So if you remember that on the first example of draw image where we drew a single image, we just did image and then an x and y value. But when we are trying to draw an animated sprite, we're going to specify the image, and then we go through and have 4 parameters corresponding to the source and 4 parameters corresponding to where and what we want to draw. So that's the sequence or order of those parameters of the draw image function. 4 properties for the sprite sheet, 4 properties for the canvas. Now typically you are copying pixels from your sprite sheet, and then when you're drawing them into the canvas, you're drawing something the same kind of size and shape. Thus, we are seeing frame width and frame height reused both times. It makes sense to do that. Screw with that and you take your own fate into your own hands, and I won't take responsibility for it at that point. So you're on your own then. So if we look at it, we'll see right now, it draws the image the first time. Then what happens is our X position on the sprite sheet is going to be adjusted by the width of the frame. So it's going to shift it over 1 column. So this shifts over 1 column. And then we will take our current sprite and update it by 1. So current sprite starts at 0. Then we add 1, 2, 3, 4, 5. And it says if current sprite is greater than or equal to the total number of sprites, 12, then we reset SX and SY to 0 and reset current sprite back down to 0. So we do that. Otherwise, if SX plus the width of the frame is greater than the width of the image, so this would be now we've exceeded our width of our image. So we can migrate through. So we SX grows, we update our sprite, then we see if we've exceeded our current sprites, blah, 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 go through, done. Now we're going to move into version 2, which is better. If the current sprite is greater than the total number of sprites minus 1, that's the same as greater than or equal to total sprites, I suppose, we reset the current sprite. I was playing with it last night. I used we have when we're accessing pixels in our sprite sheet. Pixels are whole numbers. They are not fractional numbers. It's to prevent any type of math errors from occurring. We can't say SX and SY we're copying from 6.23 on our sprite sheet as our X location. It could be 6, it could be 7, but pixels are whole entities. The canvas can subdivide them, but the graphic file itself, a pixel is a whole number. We can't use fractional ones. So I used parse int, which is a way of converting any type of math value that did not come out as a whole number and rounding it down. As I was reviewing some things this morning, we could also use the same concept of math.floor. It performs the same operation of rounding down. There's some other more advanced kind of super geeky programmer ways of rounding down that actually work really, really fast, but we're not going to go there today. We'll stick with ones that are still semi-intelligible. So when our current number of sprites maxes out, we reset it back to 0. Now what this is going to do is it's going to cycle through current sprite modulus the number of columns. It's going to give us a number 0, 1, 2, 3, 4, or 0, 1, 2, or 3, and then we times that by the frame width to determine our X location. So we can use our modulus to get our values of 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and then we times that by the frame width, and then that gives us our X location. Our Y location, we take our current sprite, divide it by the number of columns, and then times it by the frame height. Now the reason, so knowing that current sprite starts out at 0, 0 divided by the number of columns, which is 4, gives me a frame, and then multiply it by the frame height, that tells me my initial Y value. So now if current sprite becomes 1 divided by the number of columns is going to then rounded down is still going to work out to be 0. And we keep rounding it down through our first 4 iterations. So now current sprite 2 divided by number of columns 4, that is 0.5. Rounded down gives me 0. And then 3 divided by the number of columns, rounded down is 0.75. That's still, or rounded down is 0. So I keep maintaining my Y the first 4 times in my top row. Then when current sprite is equal to 4, 4 divided by 4 is 1. 1 times my frame height effectively moves my SY position down a row on my sprite sheet. And it's going to then, because it keeps rounding down, so 5 divided by number of columns will be 1 point something, rounds down to 1. And it goes through and through and through, and then it gets 5, 6, 7, and then when we get to 8, 8 divided by 4 is 2. That now bumps me down yet one more row, and then each iteration, 8, 9, 10, 11, are going to then, divided by the number of columns, keep rounding down to 2, and 2 times my frame height keeps my Y position in that then third row. So that's the magic trick that's going on. We use the modulus for our X, we use division for our Ys, and we're able to then effectively navigate through the sprite sheet. Whoever figured this out is genius, and I thank them because it's tidy, it's clean, and it works. Current sprite starts at 0, then we set it equal to when current sprite is 1 modulus 12. That gives me a remainder of 1. And then we 2, 3, 4, and we go through. And then that will actually make current sprite follow our pattern of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's reusing that modulus operation. So it's a little bit, it's very similar to utilizing where we check current sprite greater than total sprites, reset it, and then we're adding the sprites. So we can even cut those lines of code down using modulus. So this is a pretty close to the most kind of condensed way of doing it. Now, if you want to not do it in this manner using the modulus and all this fanciness, if you want to do it with greater clarity so that you're using it where you can see what's really going on, I would say that's good, because it helps you to better understand it. It's possible when doing coding to do things that generate great efficiency of code, very few lines of code, but you look at the code and unless you're really experienced in it, it just is mind-boggling. It leaves you going, I have no clue. It seems like it's obscuring it, making it harder. And when that's happening, that's not a good thing. So with that, I would encourage you to think about wanting to use verbose code so that you're not caught in that confusion, that difficulty of, oh, I have no clue what it's doing. Just using a formula or algorithm for the sake of using it because it works is great from an, because you get something done. But to continue your progress and development, having an understanding of it is often more important. So if you want to use the verbose code because it's easier to understand, I would encourage you to do so. If you like the really kind of tidy code, keep working with it so that you can wrap your brain around it. I like the tidy code, but I've been playing with it for a while, so to me, it's not so confusing anymore. But as I said, when I first stumbled on this method, I couldn't make sense out of the math. I knew it worked, and I accepted it. I moved on and solved other programming problems and just figured at some point my brain would understand it. And it does now. But in the beginning, I was left just utterly confused. So I get that feeling, that situation. Good luck.